And welcome back to another LeetCode video. Today we're looking at one of the two easy problems in the LeetCode 150 list that are easy in the geometry and math section. It's a LeetCode 202 happy number, and we're supposed to write an algorithm to determine if a number n is happy or not. And a number is happy defined by the following process. Starting with any positive integer, replace the number by the sum of the squares of its digits. Repeat the process until the number equals 1, where it will stay, or it loops endlessly in a cycle which does not include 1. Those numbers for which the process ends in 1 are happy. Return true if n is a happy number and false if not. And here we have an example where we have the number 19, and the output in that case is true. And the reason being that if we have 19, we add the square of its digits, we get 82. Now if we repeat that process, we go to 68, do that again, we go to 100, and then we land at 1. Now the second example where n is 2, well, it's just false. And why? Well, 2 times 2 becomes 4, 4 times 4 becomes 16. Actually, let's write that out. So if we start at 2, we go to 4, right? Sum of the square of its digits is 4. Then it's 16, then it's 1 plus 36, which is 37. That becomes 3 times 3, which is 9, plus 7 times 7, is that 49? So that is equal to 58. Now we continue with, well, what do we have? 25 plus 64, which is equal to 89, right? Taking 6, 89. That becomes 8 times 8, 64 plus 81, which is 145, is it? Oh no. 145. That becomes 1 plus 16 plus 25, which is, well, 42, if I'm not mistaken. 25 plus 15 plus, right? 42. That becomes, what does it become? 4 times 4 is 16. 4, which is 20. And then it becomes, well, 2 times 2 plus 0 times 0 is 4. And now we have a cycle. I hope the math was right. But yeah, so that leads to a cycle, which is why n equals 2 is not a happy number. Right. So, well, since this is an easy problem, we probably have to, if you don't see a closed formula right away, you probably have to just implement the process, which for us means we have to implement a little helper function, sum of squares of digits, which I will implement in this case. And yeah. So let's just do this real quick. So we have this helper. So how do we do it? While I'm going to rename this to m. While the number is larger than 0, and by the way, we're only dealing with positive values, and they're also going to be always larger. 1. So while m, what do we do? Well, we get the digit. That's m percent 10, so modulo 10. Then we're just going to divide m by 10, which equals a right shift in decimal notation. Digit. Right. So that's what we do. We add up the digit squares. That is our little helper function. Now, to be able to detect a cycle, right, we have to keep track of what are the numbers that we computed. So what we could do is we could say have a set while, and then we do the loop. So while n not in scene, so we check if n is equal to 1, right? Then it's a happy number. Return true. And otherwise, just going to add our number to our scene set, and we're going to update our number by computing the sum of the squares of its digits. Then at the very end, we just return false when n was found in scene. So if we run this, we get the correct result. And if we do a space and time complexity analysis, let's see, time and something space. So it depends entirely on how long these cycles can be, right? And I don't know exactly how long these cycles can be. However, somebody else knew it, and it's definitely less than n. There's probably a tighter lower bound, a tighter upper bound, I'm sorry. You can look it up if you want to. Because I don't see right away why, for example, these sequences are not diverging to infinity. Why they always converge or stay in a loop, and why these loops can't be larger than n or even some other value. But what is cool is that you can actually reduce the space complexity. So right now we're using the scene set, right? And I don't know if you remember from the linked list problems where you have to identify a cycle in a linked list. But there we had the idea of a fast and a slow pointer, which is exactly the same idea that you can apply here. And the intuition is that, actually, let's go to the drawing board. If you have a cycle of numbers, or let's just say, not very good. You have a linked list that has a cycle like so. And you don't know where the cycle starts, right? It can start anywhere. But the idea is that you have a slow pointer and a fast pointer, and they both start at the same starting position, but then the fast pointer, slow and fast, the fast pointer will always advance 2 steps, will advance 2 steps, it will advance 2 steps, and the slow pointer will only advance 1 step at a time, as you can see. So this will be at 1, T2, T3, and the slow pointer will just go T1, T2, T3, T4, 5, 6, and the fast one will, so this is the 3 for fast, this is 4, so they're not meeting yet. But now this will be 5, T5, fast. So at T5, they both meet at the same node, and that is how you detect the cycle. So the fast pointer advances 2 steps, the slow only 1 step. And at some point, it's guaranteed that they will run into each other, regardless of whether the cycle has an even or an odd length. Simply because of the fact that one goes twice as fast, it's guaranteed that they will run into each other. So we can use the same idea here, but instead of iterating over list nodes, we're going to use the values themselves, right? Well, fast unequal to slow. We're going to iterate, and yeah, we're just going to compute the fast value and the slow value. And the slow value gets only updated once, and the fast value will update it twice, which is pretty much the same. So fast. So if fast is equal 1, we return true. And that's pretty much it. Now what we've done is we've reduced the space complexity to constant space. And the time complexity still depends on the maximum length of the cycle, or the maximum iterations to reach 1. See? So if fast, well, we need to be sure that we catch, the fast pointers at the right position. So if we start at 1, so we have to check now. We have to check, I believe, here and here. Let me see. Or we can just move this, I guess we could move this outside of the loop. So we compute fast twice, slow once. And then at the very end, we check, well, if fast equal 1, return true. Otherwise, we return. So this loop will terminate either when fast and slow are the same, which means we're in a cycle, or when fast and slow reached 1, right? So then we could return true. So let's try this approach. I think that's maybe a little easier. But why is this still false? I don't understand. Oh, I know why. Because we're actually not doing anything inside the loop, because fast and slow are the same value to start with, right? So we could say, we could just do this. Just advance fast by 1 step in the beginning. That'll solve that that issue for us. Right, okay. Okay, cool. So it pays off to pay attention to detail. So let's submit this, see if it passes. And it does, right. So yeah, I think this is cool that you see the fast and slow trick here again. So when it's about cycle detection, think fast and slow will help you to reduce the space complexity. And with let's actually check maybe some other solutions. Maybe we can find some hints regarding the time complexity analysis. What is the correct analysis? Let's see. Step by step of 1 space, we have that. Complexity, oh. Complexity O log n. Approach complexity O log n per digit sum operation, and since the values eventually fall into a cycle of smaller numbers, we treat the number of iterations as a constant. Really? Well, that doesn't make any sense, because you don't know how large the number is, right? So it's, I mean, you could argue that anything is constant when you know the value of a number. You know, does this length of the cycle not depend on what the starting value of n was? No, well, he can't say that. So I don't, that's not a good analysis. Anything else we have here? Recursion solution, that's, easy Python with log n. Time complexity not explained. Well, yeah, so apparently it's not that easy to reason about the time complexity here. If you wanted to figure that out, I suppose you would have to manually by hand look at some examples to see if you see a pattern of how large these numbers can get. And because if you start at, I mean, here you can see we start at 19, it goes up to 82, then it goes up to 100, then falls to 1. So I don't know what the pattern here is. So the time complexity of n, question mark.